Good evening to one and all present over here. Today I'm going to present my 11th video. So the video with this I'm starting a playlist entirely for microcontroller based system design. As of now we will be covering the topics that are given in Anna University Regulation 2017 EEE syllabus, which is having a subject code EE6008. Later on we'll be adding according to the various university syllabus and curriculum. So with this basic introduction, let me go into my topic. So this is the thing. So the name of the subject, if you're going to see means, it is EE6008 microcontroller based system design. So today we are going to start with the fourth unit. You may not get panic upon seeing this. Initially, we'll be going with this fourth unit, and in my upcoming videos, I'll be adding the remaining 4 units topics. So this will be very, very useful for the persons who are having a first time experience with this particular subject, and it will also be very, very easy when you are going to prepare your subject during the 11th hour. That means before the examination, when you are not able to understand a concept, this will be very, very useful. So unit 4, if I'm going to go with, means it will be dealing with introduction to ARM processor. So ARM architecture, ARM programmers model, ARM development tools, memory hierarchy, ARM assembly language programming, simple examples, architectural support for operating systems. So these are the topics that we will be seeing in this particular unit. Today to start with, we'll be going with ARM architecture, the first topic. So here we'll be dealing about the various hardware features supported by the ARM processor architecture. So here if you go with ARM means initially it was called as Acorn RISC machine. Later when it was investing itself in the stock exchange, it was changed from Acorn RISC machine to advanced RISC machine. So RISC is nothing but a reduced instruction set computing. Here for a given instruction there will be lesser number of hardware operations involved. So the hardware operations, they are called as a micro operation, and the instruction is called as your macro operation. If a given instruction has lesser number of hardware operations involved with it, it is called as your reduced micro instruction set computing or reduced instruction set computing. So micro operations are the set of hardware operations associated with the instruction. Hardware operation means moving a data from one register to another register, moving a data from a memory location to a register, moving a data from a register to a memory location, adding the contents of 2 registers, storing the result of an operation into a register, reading a memory location, writing into a memory location. All these are called as your hardware operations. So for the time being, just to understand, micro operations are the set of hardware operations associated with a given instruction. So reduced instruction means it will be having lesser number of hardware operations, lesser number of micro operations for a given instruction. Next one, it majorly supports load and store architecture. Load and store architecture means the instructions will be data processing instructions will be predominantly acting upon only register data. So any data which is present in a memory location will be first transferred to a register. Operations will be performed on the contents of the register by the arithmetic and logic unit. Result will be generated by the arithmetic and logic unit. It will be stored again in one of the register. From the register, it will be transferred to a memory location. This is called as your load store architecture. Load means transfer a data from a memory location to a register. Store means transfer a data from a register to a memory location. Here is the physical understanding of the concept. Here from the memory, first we are loading it. This is the operation we are performing. A is equal to B plus C into D. Here A, B, C and D, they represent one of the 4 locations present within a memory. which is holding a particular value. So first one, what we need to do means we need to perform the product of these two numbers, add with B. Finally, the result of the addition operation will be stored into A. So first what we are doing means we are transferring the contents of C and D into two registers over here. C is transferred to the register R1. D, it is transferred to the register R2. Here we are not transferring a location value, we are transferring the data present within a location. The content of location C is transferred to R1. Content of location D, it is transferred to R2. Content of location B, it is transferred to R3. So initially what we are doing, we are performing a load operation, transferring a data from a memory location to a register. Now we will be applying BODMAS rule over here, bracket of division, multiplication, addition, subtraction. So whenever I am performing this operation, anything which is present within the parenthesis must be performed first. So first C into D. That means R1 into R2 must be performed. This result is stored in a temporarily in a register called as R4. Then what we are doing, we are adding the contents of R4 with R3 and the result is stored in another register called as R5. The addition operation of R4 and R3, it is stored in the register called as R5. From the register R5, it is stored into a memory location called as C. So this is called as your load operation. This is called as your store operation. Transferring a data from a memory location to a register is called as your load operation. Transferring a data from your register to a memory location is called as your store operation. So this is supported by the ARM processor, load, store, micro architecture. Next one, it supports three different types of data. One is called as a 8-bit data, 16-bit data, and 32-bit data, and they are signed and unsigned versions. So generally in a memory, all the memory locations can hold only 8-bit of data. Any location if you take in a memory can hold only 8-bit of data. Suppose if I want to store a 16-bit data means I have to store it in 2 consecutive memory locations. If I want to store a 4-byte data means I have to store it in 4 consecutive memory locations. So this is the basic condition associated with the storage of data. So here in ARM processor, an 8-bit data is called as a byte, a 16-bit data is called as your half word, a 32-bit data is called as your word. So generally, whenever a data is having number of bits greater than 8, whenever a data is having number of bits greater than 8, we will be grouping the data in terms of bytes. So a 16-bit data will be viewed as a combination of 2 bytes. A 32-bit data will be viewed as a combination of 4 bytes. Here, when I am going for a higher order byte data, that is 16-bit data, 32-bit data, 64-bit data, the least significant byte will be determining the starting address of the data. Suppose I want to store a 16-bit data into a location, what should I perform? Suppose if I want to perform a 32-bit data, that means I want to store a 32-bit data into a memory location, what should I perform? That we will see it now. So generally before going into the concept of memory storage, we need to first know what is the basic format for a byte or a half word or a word. A byte means a combination of 8 bits or a combination of 2 hexadecimal digits. A 16-bit data means a combination of 16 bits or a combination of 2 8-bit data. In the combination of 2 8-bit data, this rightmost 8 bits is called as your least significant byte. The leftmost 8 bits is called most significant byte. I am coming for a 32-bit data. It is a combination of 4 bytes. Here the rightmost 8-bit data is called as your least significant byte. Leftmost 8 bits is called most significant byte. This X can be any combinations of zeros or ones. Example, how does it look like? I'm going to just provide the format of a byte, half word or word. You will not be able to visualize it, but how do we actually represent it? For example, take this number. X represents, it is a hexadecimal value. So 65H, combination of 2 hexadecimal digits is nothing but equivalent to 1 byte. Combination of 4 hexadecimal digits is nothing but equivalent to 2 byte. Combination of 8 hexadecimal digits is equivalent to 4 byte. Here in the 16-bit data, this 2654, 54 is called as your least significant byte, 26 is called as your most significant byte. Here in this 32-bit data, AB is called as your least significant byte, 45 is called as your most significant byte. So these are the various ranges associated with a particular data type supported by the ARM architecture. So any byte, it can have two format specifier. It can be either supporting both positive values and negative values, or only positive values. If it is going to support both positive as well as negative integers, means it is called as your signed data type. If it is going to support only positive values, means it is called as your unsigned data type. So accordingly, we'll be having signed byte, unsigned byte, signed half word, unsigned half word, signed word, unsigned word. So here we are representing what are the size of each of these data types. Byte means 8 bits, half word means 16 bits, word means 32 bits. Based upon the format specifier, the range of data will be varying for each of these data types. If it is going to be signed, it will be a signed byte means it will be varying between -128 to +127. Both positive as well as negative values are supported if it is a signed data type. Unsigned data type means only positive numbers alone are supported. Here the right columns represent the names of these data types that are followed in programming languages such as C, C++, Java and Python. Next one. ARM supports two different types of instruction sets. An instruction set is the set of operations that could be performed by a processor. Set of operations that could be performed by a processor is called as your instruction set. So two types of instruction sets are supported by the ARM processor microarchitecture. One is called as your 32-bit instruction set architecture, that is called ARM instruction set. Another one is called as your compressed 16-bit instruction set called as thumb instruction set. This ARM is specifically for performance-oriented applications. Thumb is specifically for low cost and power consumption reduced based applications. So all the ARM instructions will be having a flag register present within its higher order 5 bits. That means between 31, 30, 29, 28, 31, 30, 29, 28. Higher order 4 bits is entirely dedicated for the flag registers. So this conditional is optional. You need not compulsorily give. Optionally, if you want, means you can include this particular field over here. This is the general format of one of the instructions in the ARM instruction set. Mostly all the ARM instructions can be conditionally executed. Conditionally executed means based upon the condition bits present between the bit 31 to bit 38, an instruction can be either executed or skipped from being executed. In a thumb, all the instructions are unconditional execution. Unconditional means as soon as the instructions gets decoded, it can go into execution stage. Whereas in case of ARM, even though an instruction is decoded, a condition has to be satisfied, then only it can execute. This condition is optional. It need not be necessarily be followed. But generally, whenever we are going with the ARM instruction set means, generally we will be going for a conditional execution. Thumb instructions means will be generally going for unconditional execution. Unconditional means the instruction format will not be having any flag registers within it. If it is a conditional execution means it will be having flag registers within it. Next one, ARM instruction generally supports 3 address format. 3 address format means within a instruction 3 registers will be present. 2 registers representing 2 source memory locations, 1 register representing a destination memory location. So totally 3 registers will be present in a instruction means it is called as a 3 address format. A register is nothing but a representation of a memory location. A register is nothing but equivalent to a data pointer. It is holding the data present in a memory location. So 2 source addresses, 1 destination address means it is called as your 3 address format. 1 source address, 1 destination address means it is called as your 2 address format. ARM supports 3 address format. Thumb supports 2 address format. Next one, ARM supports a variety of pipeline architectures, namely 3-stage, 5-stage, and 6-stage. In a 3-stage means the 3 stages are fetch, decode, and execute. In a 5-stage means the stages are fetch, decode, execute, data memory access, write back. In 6-stage means fetch, issue, decode, execute, data memory access, write back. So what do we mean by a fetch? What do we mean by these stages? Let us just see. So here, this is the pictorial view of your 3-stage pipeline. So these are the 3 stages that will be going, that instruction will be going through: fetch, decode, and execute. So, but why do we call this as a pipeline? Means when a first instruction is fetching, means reading an instruction from a memory. Decoding means understanding the meaning of an instruction and generating the control signals. An instruction is actually a signal for enabling a particular hardware device. For example, add instruction means it will be enabling the arithmetic logic unit for performing addition operation. Subtraction instruction means it will be generating a enabling signal for the arithmetic logic unit to perform a subtraction operation. Multiply instruction will be generating an enabling signal for enabling the multiplier to perform an operation. So decode means generating a control signals for a particular hardware component present within a processor chip. Execute means the arithmetic logic unit will be either performing the arithmetical operation or it will be performing a logical operation. So in fetch, when the first instruction is fetched from the memory, and when it is going into the decode stage, the second instruction will be fetched. When the second instruction is fetched from the memory and it is going into the decode stage, third instruction will be fetched. So when one instruction is moving from one stage to another stage, the subsequent instruction will be fetched from the memory. Fetching from the memory means reading the instruction from the memory. So at a instant, if you see, means 3 different instructions will be in 3 different stages. For example, see over here, when the third instruction is being fetched from the memory, second instruction is being decoded, first instruction is being executed. Execute means performing a arithmetic or logical operation. Decoding means receiving an instruction and generating the appropriate control signals for enabling the appropriate hardware components. And finally, fetching, it means to read an instruction from a memory. So this is called as your 3-stage pipeline. 5-stage pipeline means it will be included 5 stages within it: fetch, decode, execute, memory access, write back. In the previous slide, you might have seen prefetch buffer. Prefetch means whenever one instruction is going from fetch stage to decode stage, the subsequent instruction will be fetched. So that is called as a prefetch. Prefetch means while one instruction is decoded, the subsequent instruction will be fetched from the memory. So that instruction, it has to be temporarily stored in one particular memory. That is called as your buffer. So the memory location or the temporary location which is going to hold the prefetched instruction is called as your prefetch buffer. Similarly, if you see over here, write buffer means the arithmetic logic unit will be performing a arithmetic or a logical operation. It will be generating a result. That result, it will be temporarily stored within a write buffer before being transmitted to the data memory. That is called as a write buffer. So write buffer or a prefetch buffer are a temporary small memory locations for holding the instructions or data. A prefetch buffer is used for holding the instruction fetched from the memory while one instruction is in the decode stage. A data write buffer will be holding the data that is coming out from the arithmetic logic unit before it is being transmitted to the data memory. So these are the process which are being mentioned within the square brackets indicate the processor which is implementing this particular pipeline in it. ARM7 is implementing 3-stage pipeline. ARM8, ARM9 strong arms will be implementing 5-stage pipeline. ARM10 is implementing a 6-stage pipeline. Here one thing to say over here means actually strong arm is not a processor that was developed by ARM processor. It was developed by Intel as a competition to ARM. So strong arm is the name of the Intel processor that was developed by Intel as a competition to ARM. ARM7, ARM8, ARM9, ARM10 were all developed by ARM company, whereas strong arm was developed by Intel. So here if you see means when the first instruction is fetched and moving into the decode stage, the second instruction will be fetched. Second instruction, when it is going into the decode stage, third instruction will be fetched. Third instruction going into the decode stage, fourth instruction will be fetched. Fourth instruction going into the decode stage, fifth instruction will be fetched. So at one instant, if you see, means 5 different instructions will be in 5 different stages. Fifth instruction in fetch, fourth instruction in decode, third instruction in execute, second instruction in memory, first instruction in write back. This is called as your 5-stage pipeline. 6-stage pipeline means the number of stages will be keep on increasing. This is fetch, this is issue, this is decode, this is execute, this is memory access, this is write back. So what is the meaning of issue means as soon as the instruction is fetched, here it will be directly going into generating the control signals for the instruction. But issue means it will be sent to the decoder only after certain conditions have been checked and it has been verified that the instruction could be decoded for being enabled. For example, the registers of the registers must not be occupied by another instruction. For example, if I want to issue one instruction means when I want to send a instruction to the decoder for generating a control signal, I must first ensure that whatever registers that have been mentioned in a given instruction are free. Only after this condition is satisfied along, I have to send it to the decoder. Without ensuring if I am going to send it to the decoder, it will be generating hazards. So that is called as your data dependency. That is one of the serious issue existing in many of the pipeline architectures. So the instruction issue means a fetch stage, the instruction that will be in fetch stage will be going into the decode stage only after certain conditions have been found to be satisfactory. That means the registers present within a given fetch instruction must be free. The corresponding execution unit must be free. Everything will be first checked. Once it is found to be satisfactory, the instruction present in the fetch stage will be transferred into the decode stage. That is called as instruction issue. Here if you see means when the first instruction moves from fetch stage to the issue stage, the second instruction is fetched. Second instruction moves into issue stage means third instruction is fetched. Third instruction moves into the issue stage means fourth instruction is fetched. Fourth instruction moves into the issue stage means fifth instruction is fetched. Fifth instruction moves into the issue stage means sixth instruction is fetched. So 6 different instructions will be in 6 stages. Sixth instruction in fetch stage, fifth instruction in issue stage, fourth instruction in decode stage, third instruction in execute stage, second instruction in memory access stage, first instruction in write back stage. So this is called as your 6-stage pipeline. Next one. It supports 2 different types of memory storage formats. One is called as your Little Endian, another one is called as your Big Endian. Little Endian means the data will be started to store from smallest memory address towards the highest memory address. In Big Endian means the data will be started to store from highest memory address towards lowest memory address. Let us just see both of them. So this is for, we'll be discussing this Little Endian and Big Endian for 16-bit data and a 32-bit data. Consider these 2 16-bit data over here, 3268, 5478. So this kindly understand. So this is the ultimate concept of your Little Endian. The least significant byte of your data will be determining its starting location. A data starting location for storing a data will be determined by the location where its least significant byte is stored. Least significant byte will be stored in a location which is a multiple of 2. Most significant byte will be stored in a location which is not a multiple of 2. So consider these 2 data, 3268, 5478. Here 68 is the least significant byte, 32 is the most significant byte. Similarly for this data, 78 is the least significant byte, 54 is the most significant byte. I am considering 4 memory locations over here. So 0x54326542434445. So I said 2-byte alignment means the least significant byte will be stored in a locations which are varying as a multiples of 2. So any data, any binary value which is varying as a multiple of 2 will be having its least significant bit 0. So now, since I need to concentrate only on this, I'm just considering the binary equivalents of these least significant digits, least significant value of 2, 3, 4, and 5. So for 2, the equivalent binary value is 0, 0, 1, 0. For 3, it is 0, 0, 1, 1. For 4, it is 0, 1, 0, 0. For 5, it is 0, 1, 0, 1. So 68 will be stored in the location 42. 32 will be stored in the location 43. Least significant byte is stored in a location whose least significant bit is 0. So any binary value which is having the least significant bit to be 0, it is a multiple of 2. So next, if you go for this data, 54, 78, 78 is stored in the location 44, 54 is stored in the location 45. So 4, the equivalent binary value is 0, 1, 0, 0. Here also, if you see, means the least significant digit 0. So here it is a multiple of 2. 4 is a multiple of 2. So 78 is stored in the location 44. 54 is stored in the location 45. So the data will be filled in the smallest memory location towards the highest memory location. This is the basic concept. Next for a 32-bit data. So these are the two 32-bit data, 7, 8, 5, 4, 3, 2, 6, 8. Another one is A, B, C, D, E, F, 9, 8. So here, the 32-bit data, the least significant byte of your 32-bit data will be stored in a location which is a multiple of 4. In a case of a half word, the least significant byte will be stored in a location which is a multiple of 2. Here, the least significant byte will be stored in a location which is a multiple of 4. So these are the memory locations I'm considering, 44 to 4B. So here 78, 54, 32, 68. 68 is the least significant byte. 78 is the most significant byte. So 68 is stored in the location 44. So here we are considered only about the least significant digit, which is 4, 5, 6, and 7. The equivalent binary values are mentioned over here. So 68 will be stored in the location 44. 32 will be stored in the location 45. 54 will be stored in the location 46. 78 will be stored in the location 47. So next, when I'm going to give this data, the 9A will be stored in the location 48. So 8 is a multiple of 4. How do I find it? The least significant 2 digits are 0. In 4, the least significant 2 digits are 0. So any binary value whose least 2 significant digits are 0 is a multiple of 4. Any binary value whose least significant digit is 0 is a multiple of 2. Next one, EF will be stored in the location 49. CD will be stored in the location 4A. AB will be stored in the location 4B. 9A is stored in the location 48. Here 8 is given by the binary value 1000. In this 1000, the least 2 significant digits are 0. In 44, if you see, the least 2 significant digits are 0. So 8 is a multiple of 4. So the least significant byte will be stored in locations which are varying as multiples of 4. Next one, big Endian. Least significant byte will be stored in the highest address. Most significant byte will be stored in the least address. Here also we'll be forming the byte alignment, boundary alignment. Again, consider these two things, 32, 68, 54, 78. So these are the 4 locations I'm considering, 44, 43, 42, and 41. So these are the equivalent binary values of the 4, 3, 2, and 1. 68 will be stored in the location 44. 32 will be stored in the location 43. Least significant byte at highest address, most significant byte at lowest address. Similarly, come to this 54, 78. 78 will be stored in the location 42. 54 will be stored in the location 41. Least significant byte, highest address, most significant byte, lowest address. So the locations, the data will be filled from highest memory location towards lowest memory location. Here also we'll be following the byte alignment concept. This is the same thing that is being repeated for the 32-bit value. So Here 68 will be stored in the location 48, 32 in 47, 54 in 46, 78 in 45. When coming to this data, 9A will be stored in the location 44, EF will be stored in the location 43, CD will be stored in the location 42, AB will be stored in the location 41. ARM supports these two types of byte organizations, memory organizations. So as far as your ARM is concerned, there are two operating instruction sets. One is called ARM instruction set, another one is thumb instruction set. Within that, there are six operating modes supported. First one is called user mode, where you will be writing all your C, C++, Java, Python programs. Only in user mode only you are able to write a program. You cannot write a program in the remaining modes. IRQ mode means it will be providing interrupt service for the various peripheral devices. So it is a IRQ, to be very precise, means it is a lower priority, level sensitive, vectored, maskable, non-critical interrupt request from the external device. An interrupt itself means it is a signal generated from the external device to grab the attention of the processor. So up to 32 requests can be received by the ARM processor, lower priority interrupts. Level sensitive means it will be activated either at positive level or at the negative level. Vectored means the interrupt address is predefined. The interrupt service routine address is predefined. Maskable means it can be enabled or disabled by a particular instruction. FIQ means for time critical interrupts. That means whenever a network is receiving a data, it will be generating an interrupt. So whenever a data has to be transmitted from your PC to a network, that is also a time critical thing. So time critical interrupts will be processed by FIQ mode, fast interrupt request. To be precise, it is higher priority, level sensitive, vectored, maskable, time critical interrupt request from the external devices. So in this IRQ and FIQ, it will be handling the interrupts coming the external device. In supervisory control mode, SVC means supervisory control mode. You can access all of the hardware components present within the ARM processor, internal and external. Abort mode means it will be indicating memory faults. For the time being, just to go with the terms. In the later topics, we'll be discussing what is meant by a memory fault, how it is being generated, and how do this ARM processor takes care of such incidents. Undefined mode means it indicates an instruction which has been occurred. That means the instruction which it has fetched from the memory is not present in the ARM instruction set or in the thumb instruction set. For example, whenever a hacker is doing any form of misoperation, that means he is trying to change the hardware operation, he will be sending an instruction, means only if the instruction is complying with any of the ARM instruction or thumb instruction alone, the ARM processor will be accepting the instruction, or else it will be discarding the instruction. That is called as undefined instruction mode. Whatever instruction it is fetching from the memory, it will be first checking whether it is present within the instruction set architectures of ARM or thumb. Only if it is present, it will be allowed to go to further stages. This is actually performed by the decode stage of the ARM processor. It will be classifying whether an instruction fetched from the memory is actually an instruction belonging to the ARM instruction set or thumb instruction set, or it is not belonging to any of these instruction set. Next one, an ARM processor, it has totally 37 registers, 32-bit registers. All the registers are 32-bit registers. It implements a concept called as register banking. Register banking means creating multiple copies of a register. Next one, almost all the data processing instructions will be executing within a single clock cycle. That is the basic condition for your pipeline. So this is your visible, this is your programming model of your ARM processor. Programming model means these are the set of registers that could be accessed in a particular operating mode of your processor. If I'm going to go with the ARM processor, means 16 registers could be accessed. R0 to R15 along with CPSR, current program status register. R15 will be acting like a program counter. If I'm going to go with the FIQ mode, R0 to R7 is the general purpose register. R8 to R14 will be acting like a special purpose register specifically for the FIQ mode. And SPSR, saved program status register. Similarly, if I'm going to go with SVC mode, supervisory control mode, R0 to R12 are general purpose registers. R13, R14, SPSR, special purpose registers. If I'm going to go with the abort mode, it is also the same. If I'm going to go with the IRQ mode, it is also the same. If I'm going to go with undefined mode, it is also the same. So in 4 modes, R0 to R12 will be accessible by the user. R13, R14, SPSR will not be accessed by the user. It will be acting like a special purpose register. So here the registers which are not been mentioned means it could be accessed by the user. Here which are provided in the gray, it could be accessed only in system mode. Only when the processor is going to switch from the user mode to switch mode alone, these registers which are present in gray can be accessed. Otherwise, they cannot be accessed. These are the set of registers that could be accessed in ARM instruction set mode. So I'm saying 37, 32-bit registers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37. So totally 37 registers could be accessed in ARM instruction set mode. What about thumb instruction? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So here the things registers which are present in gray, they cannot be accessed in the user mode. The registers which are not shaded, they could be accessed in user mode. Here in R13 will be acting like a stack pointer, R14 will be acting like a link register, R15 will be acting like a program counter. So R0 to R7 is called as your low register in thumb instruction set mode. R8 to R15 is called as your high register in thumb instruction set mode. Along with this 16 registers, the current program status register also could be accessed. This R8, R9, R10, R11, R12 and the CPSR, they are called as shadow registers. Next one, ARM provides a on-chip coprocessor called as a system control coprocessor. The coprocessor number is CP15. Its main purpose is it will be controlling the on-chip cache and off-chip cache. Memory management unit, memory protection unit, write buffer. Write buffer is the one which is accessed during data memory access stage. Prefetch buffer, it will also be controlling the buffer which is used during the fetch stage. Branch target cache means during the fetch stage itself, the processor will be determining whether the subsequent instruction is a branch instruction or not a branch instruction. This is for improving the pipeline processing speed. System configuration signals means read, write and various system component based signals that also will be controlled by the coprocessor. Mainly it will be performing floating point operations, digital signal processing based applications, hardware acceleration based operations. Everything will be carried by this system control coprocessor or CP15. Next one, ARM provides support for memory mapped peripherals. Memory mapped peripherals means the peripheral device will be having the address length similar to a memory locations length. For example, if the memory location is identified by a 32-bit address, the peripheral device or the IO device also will be identified by a 32-bit address. This will be reducing the number of separate address spaces to be allotted for your memory and peripherals. ARM supports only memory mapped peripherals, not IO mapped peripherals. If you go for 8085, it supports both. If I'm going to go for a IO mapped peripheral means I'll be having a separate instruction for the IO device access. For example, if you go for 8085, you'll be having in accumulator, out accumulator. In accumulator port number, out accumulator port number. In memory map, I'll not be having a separate instruction for the IO device access. It will be just accessed like just another memory location. That is called memory mapped peripheral. Next one, it supports two different types of cache organization. One is called as your von Neumann cache organization. Another one is called as your modified Harvard architecture based cache organization. So as far as your memory hierarchy is concerned, register is the fastest one. Next one, it is followed by cache. Next one, it is followed by your DRAM. Like that, it will be keep on going. That is called as your memory hierarchy, which you will be learning in the upcoming videos. So this is the basic block diagram schematic for your non-human cache or a unified cache, you will be having one separate memory for storing both the instructions and data, one cache for holding the copies of those instructions and data. A cache holds the copies of data and instructions present in the memory. Modified hardware cache means there will be only one memory. That memory will be holding the data and instruction, but will be having two separate cache. One cache for holding the copies of the instruction, one cache for holding the copies of the data. This organization is called as your modified hardware cache. So these are the various ARM architectural features that are required to understand the upcoming topics. Thank you.